Today we are going to illustrate linear regression with a simple example. Now let's first have a look at the first example. And here is the data, mortality data. This data taken from a certain region of Great Britain, Norway, and Sweden contains the mean annual temperature in degrees Fahrenheit and the mortality index for neoplasms of the female breast. Okay, so here the objective is to obtain the relationship between annual temperature and the mortality rate for a type of breast cancer in women. So here we have the mortality rate. So this is our response variable, and the annual temperature is the predictor. So we want to obtain the relationship between annual temperature and the mortality rate for this type of breast cancer. So how many observations we have? So we have 1, 2, 3, 4, 5, 6, 7, 8. So 8, and we have the second batch. So it's about 16. So this data set is 16 by 2. So the first step is to visualize the data and try to see what kind of pattern we have inside the data. So here we have 16 observations. The x-axis is the temperature and the y-axis is the mortality rate. And we can see there's a linear trend. The mortality rate is increasing with respect to the temperature. Now, what we want to do is find the underlying model as we discussed in the previous lectures. So how to identify this underlying model? So what we are going to do is to do the least square estimation. So underlying model is y equals to beta 0 plus beta 1 x plus epsilon. And we assume this arrow is normally distributed with mean 0 and variance sigma square. So that's why we have 3 assumptions: A1, A2, A3. So A1 is mean 0, A2 constant variance, and A3 is uncorrelated. So that is a random noise. So this is a random noise. So here, this epsilon is the random noise. So coefficients are estimated by minimizing the residual sum of squares. So here, this is the residual sum of squares. So based on the least square estimation, we are going to do the normal equation. So what are the normal equation? So take this, if we take this as our loss function, beta equals to this term, then what we are going to do is take the derivatives with respect to beta 0 and derivatives with respect to beta 1 and set both equal to 0. Then we solve for beta 0 and so this is keep jumping. Then we will be able to obtain the least square estimate. So here is the least square estimation of beta 1 hat. So if we put a hat on the parameters, it means it is an estimated coefficient. And beta 0, and we have not only the mean estimation, but also we got the variance estimation, beta 1 hat and beta 0 hat. And here the x bar and the y bar is the average of y and the average of x. Now let's have a look at the explanatory power of the model. The total variation in y can be measured by the correct total sum of squares. So correct total sum of squares is yi minus y bar and square. So it's each yi minus the average of y, all the y, and then we take the square and the sum of the squares. So this is a total variation. So this total variation can be decomposed into two parts. That is the regression sum of squares and the residual sum of squares. And this part is called analysis of ANOVA. So analysis of ANOVA is also called, analysis of variance is also called ANOVA analysis. So the fundamental idea of ANOVA is we want to decompose the total variation in the data into the part that can be explained by the regression model and the part that the model cannot explain. That is the residual sum of squares. So regression sum of squares, and that is the yi hat minus y bar. So this is a model prediction minus the average of all y's. And the residual sum of squares is each observation minus the model prediction and the sum and the square and the sum of the squares. So yi hat equals to beta 0 hat plus beta 1 hat xi is called the predictive value of the yi at xi. What is R square? R square is the regression sum of squares divided by total sum of squares, correct total sum of squares. So basically this one measures the proportion of variation in y that can be explained by the regression model. And because regression sum of squares equals to the correct total sum of square minus the RSS, so if we do a little bit, if we replace the regression sum of square with the correct total sum of square minus RSS, we will be able to get R square equals to 1 minus RSS divided by correct total sum of squares. So this gives us the proportion. R square is an indicator that gives us information about the proportion of variation in y explained by the fitted model. So the ANOVA table for simple linear regression. So here we have a new concept called degree of freedoms. So how to get the degree of freedoms? The degree of freedom, as shown here on the top, is the number of observations minus the number of estimated parameters, population parameters. So in correct total sum of squares, we have number of observation yi and minus the number of estimated population parameters, that is only 1. So this is n minus 1. And this one is n. But in yi hat, we have two parameters to be estimated, that is beta 0 hat and beta 1 hat. So that's why this is m minus 2. But over here, we don't have any observation. We only have one population parameters, so that's why this is 1. Okay? So the simple rule, degree of freedom equals to the number of observations minus the number of estimated population parameters. And this can be used in most of the ANOVA analysis. So here, xi is not a random variable. Only yi is a random variable. So that's why here xi is a predictor. Yi is the response variable. So what is the mean squares? Mean square equals to the sum of squares divided by degree of freedom. So as we can see here, this mean square, the first one, actually equals to the sum of squares. That's why, that is because we only divide by 1. But over here, we divide by, we use the sum of squares divided by n minus 2. So this is how we got the mean squares. So the ANOVA table for the breast cancer example, that is degree of freedom is how many total observation? We have 16. So this is 16 minus 1, 16 minus 2, and this is 1. And another simple rule is over here, all the degree of freedoms, if we add them together, it should equal to the total degree of freedom. So if they don't equal, then we don't have a correct ANOVA table. And same if we use the just put the xi and x bar, y and yi hat, and y bar into the equation, we will be able to get the sum of squares and mean squares. Here, this mean squares equals to 2599.53 divided by 1. And over here, 56.2 equals to 796.91 divided by 14. Okay. Now let's continue our discussion on the t-statistics. So since we got the parameter estimation, now we have the mean and variance of each parameter as each estimated parameter. So what we want to do is we want to test the hypothesis, the null hypothesis H0, whether beta j equals to 0 or not, against the alternative hypothesis beta j does not equals to 0. So here, why we are using these t-statistics? Because here we don't know the population variance. We only know the estimated variance of beta. So the t-statistics. So in general, if we want to test it on the mean variance unknown, we have this t-test statistic. So x bar is approximately normally distributed with mu and sigma over square root of n, and x bar is also approximately distributed with t distribution. So this is the central limit theorem. And here, if we don't know the population variance, and if we replace it with the sample standard deviation, this will become the t distribution. And the same here for the beta. For the beta, the mean, because we want to test beta whether it is 0 or not, so we minus 0 divided by the standard deviation of beta. Here, for x bar, the standard deviation is s over square root of n. Here, the s is the standard deviation of x. But for x bar, the standard deviation is s over square root of n. So that's why here, the t-statistic is beta j divided by standard deviation of beta j. So in t-test, the higher the value of t, the more significant is the coefficient. So for two-sided test, so in hypothesis testing, we have 3 ways to do the hypothesis testing. So what are the 3 ways to do the hypothesis testing? Classical approach, compare the t-test statistic with classical values, okay, critical values. Second one is a p-value approach. So this is a p-value approach. And the third one is confidence interval. And confidence interval is going to be in the next slide. So the p-value approach, the probability t degree of freedom, this is a t-test statistic greater than, here this is a t distribution greater than the area that greater than the observed t statistics. So this is observed value. That is if we use beta j divided by standard deviation of beta j, this is our t observation. So we have degree of freedom for the t statistic, and we have the observed value of the t statistic. So if p-value is very small, then either we have observed something which rarely happens or H0 is not true. In practice, if p-value is less than the significant level alpha equals to 5% or 1%, H0 is rejected at a level alpha. So in the confidence interval approach, so 101 minus alpha confidence interval for beta j is given by beta j plus minus t n minus 2 alpha over 2 by standard deviation of beta j, where the t n minus 2 alpha over 2 is the upper alpha over 2 point of the t distribution with n minus 2 degree of freedom. If the confidence interval for beta j does not contain 0, then H0 is rejected. So far, this is how we make the decisions. We have 3 approaches to test whether the beta j equals to 0 or not. Okay. Now let's have a look at after we estimate the parameters, and we conduct the t-test for the significance of each parameters. Now the next step is to do the model diagnostics. So model diagnostics is also called residual analysis. So this is a predicted value, and the yi is my observation minus the predicted value is the corresponding residues. So standardized residue equals to ii over standard deviation of ii. So plot of residues are extremely useful to judge the goodness of the fitted model, and we can use a normal probability plot to see whether all the residues are normally distributed. Or we can use residues versus the predicted value, or residues versus the covariate x. Those are three different ways to test the normal assumption of our residues. So this is analysis of the breast cancer data. First, we obtain the regression equation. Here, T is my predictor, M is the response, and this is beta 0, and this is beta 1. And for each predictor, this is the intercept, and this is a predictor temperature. We have coefficient beta 0 and beta 1, standard deviation of the coefficient. And this T statistic is actually, we use the coefficient divided by the standard deviation of coefficient, we got this value. And this probability, this p-value actually is what we just discussed, two-sided test, and the proportion of value, actually absolute value greater than this observed t statistics. So the standard deviation estimation is 7.54466. So the standard deviation of the residues, and the R-square values is 76.5. That means our regression model can explain 76.5% of variation in the data. Okay, and here there's a just R-square. We will talk about it later in the multiple linear regression. And here is an ANOVA table. ANOVA table, we have regression. We have one parameter, and this is n-1, 16-1. This is n-2, 14. We have sum of squares, and we use the sum of squares divided by the degree of freedom. We got this mean sum of squares. So this 7.545 is actually the square root of my residues. Okay, if we take the square root of 56.9, we will be able to get 7.54466. And this is f-test to see whether these two variances are approximately equal to each other. So we want to see whether this regression can explain most of the variation in the data. So this F statistic actually use this mean square divided by 2599.5 divided by 56.9, we will be able to get 45.67. So in other words, this statistic, F statistic, is use this mean square divided by this mean square. We got this 45.67, and we got the p-value. P-value tell us this variance is significantly different from this variance. Okay, because p-value, smaller the p-value is, the more significant evidence we have that reject the null hypothesis. So here the f-test is to test whether two variances equals to each other or not. Obviously they don't, they are not approximately in the same range. So now the fitted regression model, we got the fitted regression model. We want to do the prediction for a certain temperature. For example, if we have a temperature that is not observed in the data, we want to predict the mean of y at x equals to x0. And this can be obtained from the above model. What we mean is, we just, for example, prediction for the temperature of 49 degrees is obtained by just putting this value in 49 over here. Then we solve this equation, we will be able to get the predicted value of the mortality rate is 93.85. But here, this is only the mean estimate. At the same time, we need to get the standard error of yx0. So this is given by this equation. So how did we get this equation? Okay, this equation is actually given by this variance yx0 hat equals to variance beta 0 hat plus beta 1 hat x0. So if we solve for this equation, we get a variance. This is actually equals to variance beta 0 hat plus x0 square variance beta 1 hat plus 2x0 covariance beta 0 hat beta 1 hat. And this gives us the equation to predict to get the variance of our prediction. So as we talked before, we need an envelope, right, confidence interval between our prediction. So here we get the variance. So here this is a standard deviation, but here what we derive is the variance. We take the square root, we will be able to get the standard deviation. So since we know the x bar, x0, 49, right? And we know xi, all the xi's, and x bar, n is equals to 16. We will be able to solve for this standard error of our prediction. And this sigma hat is actually equals to the mean sum of squares of the residues. Okay, actually this is 7.544. How did we get this 7.454? Which is actually the square root of 56.9, and it's also this number 7.54. So sigma hat is equals to 7.54, and consequently we get the standard error of our prediction at the location x0. And at the same time, we can derive the 95% confidence interval for the mean response at x0, that is beta 0 hat plus beta 1 hat x0 plus minus tn minus 2, 0.025 by the standard error. Here, the 95% confidence interval for the mean mortality corresponding to a temperature 49 is 88.63 and 99.07. And here is a residual plot, and we can see that no systematic pattern is discerned, is observed. So A1 mean is 0 and constant variance, and there's no particular correlation between those points, pretty random. Okay, so linear regression assumptions, 3 assumptions: mean 0 and constant variance, and residues, each residues, they are uncorrelated or independent. So this is a random noise. Okay, so far we finished the first example of the mortality rate versus temperature. Now let's demo the this data set and the analysis using the Excel. So this is the data we just used in this example. So here, this is the temperature and this is the mortality rate. If we go back to the example, we will be able to see this is a mortality rate, this is the temperature, 51.3, 102.5, 51.3, 102.5. Now the first step is to do the scatter plot. So in order to do the scatter plot, we select the scatters. So this is what we got. The scatter plot, and the x-axis is the temperature and the y-axis is the mortality rate. Okay, and we may change the title to be simple linear regression demo mortality data. And we can see, and this data is not well positioned. It seems that we need to change the x-axis and the y-axis to the right range. So what we do is we first select the axis and we add the axis title. So this is temperature, and here is mortality rate. So if you press enter, so it will change. Now the next step, we want to change the x-axis range. So So what we do is we select format, and we select the shape and styles. And here we will be able to change the bound minimum and maximum for the x-axis. Obviously here we need 30 to maybe 55. Okay, got 55. And also for the y-axis, so we choose y-axis, we'll be able to change the minimum to be maybe let's use 50. Okay, now we got the scatter plot, and if you think this color is not what you want, and you can go to this font color, and you can also change the size. Okay, to be different data. You can even make it bold. Now, if we don't want to do the linear regression fit, we can add the trend line. And this trend line is dashed line, and you can also select to change the different lines. It can be an exponential line, linear line, log line, or polynomial line. But here, what we are trying to illustrate is a simple linear regression. So we do a simple linear fit. And we can change the width, line width, and we can change the dash type, and we can even change the color, make it red. So this is our scatter plot. Now the next step is to perform the regression analysis. In the regression analysis, we click the tab Data. There is a data analysis toolpack we can use. So let's find the regression. Click OK, and let's first choose the Y range. So this is my Y, and this is my X. And because we include the labels, so for example, if you have a look of Y from B1 to B17, so we include the labels. So we click, we have already included the labels. And we don't want the constant to be 0. We want the 95% confidence interval. And the output range, I don't want to generate a new worksheet, and I just want to put my output over here. Now, you can also choose to generate you a residual plot and a normal probability plot for the residues. So if I click OK, so we will be able to get all the statistics. And move this statistic a little bit. So this is a multiple. This is a R square 76.53.5. So in this, is it same as what we just observed here? So this is 76.5. If we go back, you can see adjusted R square is over here, and a standard error 7.554. This term is also the square root of the mean squares of the residues. And the observation, we have 16 observations. So this is n-1, 16 minus 1, n-2, 16 minus 2, and this is 1. And this is the sum of squares. And if we use sum of squares divided by degree of freedom, we got the mean sum of squares. This f is actually this number divided by this number, you got f, and automatically it will get the p-value for you for the f test. And at the same time, we will be able to get the intercept beta 0 hat and beta 1 hat. This is beta 0 hat, beta 1 hat. This is for predictor t, because we use beta 0 plus beta 1 t, right? So here, this is standard error of each beta estimation. So this is a mean estimate. This is the variance of my of each beta. So t equals to the coefficient divided by standard error. We got t, and we will also have the p-value, the two-sided t-test. And we also get the upper 95% confidence interval for each beta. So this is a confidence interval for the beta. It's over here, 95%, so alpha equals to 5%. At the same time, here that is the observation number. This is a predicted value, and this is the residues we have. So if we plot the residues, so this is normal probability plot values. So we got the normal probability plot and the residual plot, and we can see here we didn't observe any systematic patterns. The mean is about 0, constant variance, and we don't see a specific correlated pattern in this residual plot. Okay, so so far we have finished the first example on simple linear regression.